Great. Okay. So Ward is back. So let's get started. Thanks everybody for coming to this session, today's webinar on software engineering and best practices. My name is David Ball. I'm just hosting this webinar. I'm a graduate student at the University of Arizona. This is part of a series of monthly webinars on a variety of technical topics that are offered every month, and you can find a calendar of these upcoming topics at the PIRE website, which is bhpire.arizona.edu. Today's webinar is going to last 1 hour, and there'll be some time built in for questions at the end. Once this session is done, it'll become available on YouTube eventually, so you can find the YouTube link on the PIRE website as well, and all the past videos are there as well. And one thing that's really important to make sure to do is we're going to send out a survey afterwards, and it's really useful and important if you could all fill out that survey. Your feedback's really valuable to move forward. A few other just logistical things we need to cover. It's best if everyone turn off their audio to avoid background noise. Turning off video probably improves bandwidth and might make Ward's presentation a little clearer for the rest of us. And at the end, we'll have questions. And yeah, so we're really lucky today to have Ward Harold. He's a solutions architect at Google, to tell us a bit about best practices in software engineering. So with that all said, Ward, thank you for being here, and please take it away.
Okay, thanks a lot. I will do the screen share thing here. Sharing, cool. And all right. Yeah, so like David said, I'm a solutions architect for Google Cloud in Austin, Texas. I've been here about 2.5 years. Before that, I've been a developer for 30 some odd years, more years than I care to think about sometimes. Started out as my undergrad is in math. Mathematical statistics, went to grad school at Rutgers for computer science while I was working at a pharmaceutical company in New Jersey, which there are a lot of. And so while I don't have any direct experience working with doing astronomy stuff, I did spend 7 happy years supporting scientists, organic chemists and pharmacologists in a research setting. So with that, what Rosie and David had asked me to talk about was software development best practices. I shortened it down to essentials because in the course of about 50 minutes, we could cover maybe 1 or 2 best practices. And so I'm going to talk more about some essential things that I've learned over my career, things that I wish that maybe somebody had told me before I figured them out for myself. But sometimes you have to figure things out for yourself. So by nature, this is going to be kind of a survey course. And I told David that, if people have questions or want to go deeper in on a particular topic, then I certainly welcome that kind of feedback sort of in flight as we're talking. If I was in the room, I would definitely want to be looking around and asking questions and getting feedback from people as we talk, just because this is developing software is kind of very specialized to what's going on. Okay, there we go. Okay, so as far as agenda, there's basically 5 things I wanted to talk about: languages and frameworks at the beginning, and then building the right things, always testing your stuff, keeping things under control in terms of your source code and your software artifacts that you're building. And finally, and probably the most important, but sometimes the hardest thing to do in software development is actually delivering something, especially when you're you don't necessarily have a customer per se, but it's just you know, for your own research or for your department or something. Shipping sometimes gets short shrift, and people wonder why, you know, they spend all this money and they see people spending all this time on computers and they never see any results out of it. So you don't want to ever have that conversation with anybody. So we'll get to that at the end. Okay, so first up, languages and frameworks. This is kind of an anticlimax thing in that it was true 30 years ago when Fred Brooks wrote it, and it's still true today, that there really isn't a silver bullet. There's no thing there's no language, there's no framework that you're going to find that's magically going to make your software better than somebody else's, that's magically going to make your code more bug-free or easier to read or even easier to write. So there are a plethora of languages. Some of them are better than others, but every one of them has some kind of a sweet spot. Even, you know, some of the things that I will admit my own bias. I'm no fan of PHP, but I know people have built really cool things in PHP. Sorry, I'm losing my voice. This is my second or third presentation today, but anyway, I'm a huge fan of Go down here in the bottom, but I'm also, a lot of the work that I'm doing right now involves doing high performance computing, and Go would be a terrible choice to use for high performance computing, just because the numerical libraries aren't there, and I don't want to write those libraries. That's not what I'm there for. I want to work with packages that can already do, you know, solve differential equations for me. I don't want to have to write that code. And that's kind of the key, is, you know, you don't want to be writing stuff that isn't delivering value for you. The other thing that you want to be careful of is, you know, don't learn something new just to learn something new. I'm terribly guilty of that. But you know, what you know may be good enough. So the work that I do in high performance computing, Python is sort of the lingua franca in that space. So you know, Python with NumPy and SciPy are a really, really good choice, kind of the de facto choice at this point for high performance computing. But there's a new language called Julia out of MIT that's also very, very powerful. And just because I don't know Python well enough, you know, I've been able to spend some time learning Julia. If I knew Python better, I probably wouldn't spend the time to learn Julia. But you have to make those choices yourself, and you have to be aware that they always are choices, and you need to have good reasons for, you know, for abandoning what you do know and learning something new. And you really, really don't want to, you know, reinvent the wheel or force fit a language into doing something that it's really not intended to do. Having said all that, I'll say something that, you know, I might not have said 20 years ago, but it's become true for me, is that you do want to learn Bash or PowerShell. So depending on what environment that you happen to be working in, if you're working on a Linux box, you definitely want to have more than just passing familiarity with Bash. If you're working in a Windows environment, PowerShell is very powerful, and you want to use that, mostly because you're going to spend a lot of time. If you're actually doing real work, you're going to spend a lot of time, you know, in a shell, just moving things around and doing stuff. And if you're capable with Bash or PowerShell, that's going to make your life a lot easier than if you have to go or coerce GUI tools into doing things. I could regale you with many late night war stories from, you know, about how I happened to actually, you know, get pretty good at Bash, because things went awry and we had to fix them. And if we would have stayed up, you know, dragging and dropping things in Windows, we'd probably still be there doing it. But Bash and PowerShell allow you to fix those things pretty quickly. So having said that, there are a couple of things have to watch my time here. There are a couple of things that that are really important. It's not necessarily that you should definitely be an object-oriented programmer, or that you should be a functional programmer, or that you should be a C programmer. What has turned out really to be the case, and very valuable to me and to other people that are professional developers, is the idea of creating what we call composable abstractions. So programming is really all about creating abstractions, and that's a good thing, but the real value in creating abstractions comes when you're able to compose them. And if you want to read about how to do that, then there's no better place to do that than reading a book called Structure and Interpretation of Computer Programs by Abelson and Sussman. It's probably one of the best books on just pure programming that you will ever read. It uses Scheme as a thing. I think MIT now actually has online a version of the course. It's MIT's course 6.001, and they teach a version now in Python, whereas the book uses Scheme. But if you actually want to learn how to program and think, methodologically about and express those thoughts in a programming language, then that's a very good place to do it. The other thing that is essential is that you're always making decisions when you're developing software. And some of those decisions are wrong, and some of them you aren't sure of, and some of them you just want to change later because they weren't wrong at the time, but a better choice became available. Suddenly you have GPUs at your disposal, and so now you want to use GPUs instead of doing parallelism across CPUs. And so you want to have that decision hidden behind an interface that isn't going to change, or that will change minimally when you change the underlying structure. So, I mean, this sounds like motherhood and apple pie, but it really is, an essential piece of developing software. And Steve McConnell's statement will take you very far. Whereas if you get into the habit of asking, what am I going to, what do I need to hide? Or if you ask yourself, it's like, which of these decisions that I've made am I least sure about and may change going forward? And when those things rise to the top, then you want to create a stable interface around them and hide that. Okay, so that's all I'm going to say about programming languages and stuff, because programming languages change all the time. I've learned over the course of 30 some years, almost a dozen programming languages for one reason or another. And I'm not done learning. It's like, like I said, I'm just now getting into Julia and learning that stuff. So rather than, becoming a super expert in today's latest language, it's better to learn a language than to do that. I was really, really good at C++ at one point in my career, and could ask really, really hard interview questions of pretty smart candidates. And but I haven't written a line of C++ code in probably 10 years. So that was valuable at the time, but it ceased to be terribly valuable later in my career. Okay, so more important is actually building the right stuff. And the subtitle there, talk to your users, I mean that literally. A lot of people, when they write code, I don't know how astronomers are, but I know programmers, computer scientists tend to be pretty introverted, pretty private people, and they don't actually like talking to users. But that turns out to be the key to actually building good software, is you have to actually be spending time with the users, talking about what they want to do, and what kind of pain points they have. And even if you're just writing software for your own research, you need to step back and sort of think about it from the perspective of, well, what do I actually want to do with this? Since you're astronomers, you may be less like a computer scientist who just gets a kick out of writing software and making a computer do something. You guys actually want to achieve results in astronomy, whether you want to render a picture of a black hole or hunt for supernovas or whatever it is you want to do. You're doing it for a purpose, and so you need to be able to change sort of mindsets from developer to user and think about it from that perspective. So one of the key tools for doing that, it comes out of agile software development practices, they're good practices. Some people adopt it as sort of a religion, but that's usually a mistake. So you look at that and you say you look for the good. You look for the good practices, and you want to follow up with those. So anyway, user stories are a way to capture conversations with a user. So it's a requirements gathering tool of a sort, but really one of the taglines is it's a reminder to have a conversation. So you want to structure them in there's a standard structure that people use, and that's what this table says. So basically you want to say it's a who, what, why thing. So you want to know who you're building your software for. You want to know what are we building, what kind of software, and then you want to know why are you building it. And the way you structure that is as these little very structured sentences that say, as some type of user, I want to accomplish something so that I can get some benefit or value. And we can look at some examples. The first one is, for software for perhaps a ride-sharing service as a driver. So now the user is actually one of the drivers, or is actually a driver for this service. I want to block low-rated riders. So if I have people that get in my car drunk or are unruly some other way, they're going to be low rated, and I would rather not be matched with them. So I want the option for doing that. So that's a reasonable user story. I invented a couple of others that may resonate more with the scientific community. So that as a principal investigator, I want to prioritize telescope time so that the postdocs I have working for me can complete the research, because they need time on the telescope so that they can do their observations and get their data so that they can actually maybe get published or do whatever they're trying to do. And as an admin, so now you're not necessarily a researcher, but as an admin, I want to mark image collections public so that they can be freely accessible to authenticated users. And you could imagine that you may want to mark those image collections as private, or only make them accessible to certain groups of users within your facility. So you would capture all of those as user stories. Some of there's sort of a checklist over here that talks about how you want to, what's really important about the user stories. It looks easy to do. It's not as easy as you would think, but it's a thing that comes with practice, and it ends up being very valuable. So you keep them short. You keep everything as simple as possible. That's a general tenet of any kind of scientific endeavor, or in software especially. It's very important to write it from a user perspective. Like I said, have a conversation with your users, have a conversation with yourself. Think about it from the perspective of, I'm going to be using this, so what would I expect as a user? And then make the benefit clear. Do just a single thing. There's a part of a Unix philosophy that we call it in the development world, that's basically says, do one thing and do it well. A lot of software that people write, a lot of times sometimes written by professionals, sometimes written by non-professionals, tries to do a lot of things. That's generally a mistake. Even Unix tools, when I see Unix tools that have a whole plethora of switches and a little sub-language associated with them, I tend not to use that stuff. I use them for the one thing that they do really well, that I understand and I know how to do. And that's what you should strive for in your user stories. And then you want to provide acceptance criteria And rather than, going through the acceptance criteria stuff here in detail, basically you can Google all of these things and get a lot more information and go much deeper. So what I'm trying to do is sort of give you some hooks that you want to for things to go and investigate further. And user stories are certainly something worthy of your time to investigate. And when you do that, pay particular attention to the acceptance criteria. Let's see. Okay. And when we get to talking about testing, user stories are going to drive a lot of your tests. So it's really important to have a good set of user stories and to do them pretty well so that you can get your so that you can do your testing accurately. Okay, so you've got user stories and you get a big pile of user stories, and that's not a bad thing. That usually means that it's like, okay, now I have the possibility of actually building some really cool, really valuable software because I have all these requirements that I know that real users actually want my software to do, and now I just have to go about building it. Sometimes all you need is that pile of user stories. A lot of times when you're dealing with more complex software, you need more than that. And user story mapping is my favorite way to to deal with that. And this book, User Story Mapping by Jeff Patton, is very, very good. It's like one of the better books that I've read on this topic, because he actually gets into the real details of how you go about doing this stuff in the real world, and it translates pretty well. So with that, this is kind of the way that user story maps get structured. You have a set of users up here at the top, the little white boxes, the white round angles, I call them. Those are basically user personas. So they might be, the PI on a project, the admin, or a postdoc. Those might be those two boxes. You have activities that are sort of collections of things that these people want to do throughout the day, and those are collections of tasks. So they're expressed as collections of these lower level tasks things, which are kind of like groups of user stories. And the user stories are what we just talked about. And the key to these story maps is that you end up creating this narrative that goes through, a day in the life of a principal investigator, let's say, on a telescope at, in Hawaii or at Fort Davis in Texas. One of the dads on one of my kids' swim teams was an astronomer and he regularly went out to Fort Davis to do research on those telescopes out there. So this is, these narratives, and there are you can imagine drawing multiple of them through this set of user stories. That's, that captures kind of the day in the life of a PI or a postdoc or an admin, at the KEC or whatever, when they're using the software that you're looking at creating. Okay, so I'll stop there and ask if we have any questions online. I'm more than happy to answer them, and if not, I will restart my assault. Not hearing anything. So let's go on to testing. So this is another thing that's critically important, and I think everybody understands that they need to test their software. They're not always, a lot of times people say it's like, well, I need to test my software so that I know that it works right. And that's definitely true. You do write tests to validate that it's like, yeah, the computations that I'm doing are correct. These, the differential equation, the results, the solutions to the differential equations that I'm using are being computed properly, or the statistics that I'm computing across this data are working properly, or the images that I'm generating are rendering the way that I want them to do. You do want correctness. The other thing you want to know is, it's like that's a perennial problem with developing software, is like, how do I know when I'm done? And the best answer that I've found, which is why I'm kind of a true believer in this test first style of development, is to say, it's like, well, you know, you're done when all of your tests are passing. It's like, okay, well, at that point, if I've actually followed my method and, you know, written a comprehensive set of unit tests that test the requirements that I've expressed in my user stories, then when all of them pass, well, that software must be done. Now, it's inevitable that in the course of writing that software, you will have discovered other things that the software needs to do, but that's another release, and that's, you know, we'll talk about that, you know, at the very end, if I don't run out of time, because that's a point at which, you know, you incorporate the things that you learned into the next release, but you do want to release, you know, what you have and what you've completed. So we'll talk a little bit about this. Martin Fowler is one of the big advocates for test-driven software development, as is a guy named Kent Beck, who kind of invented he was one of the proponents early on of extreme programming back in the 90s. And it's a technique for I'll just read it. It's a technique for building software that guides software development by writing tests. So notice that it's not so much about actually, you know, doing the tests. The tests are important to make them pass, but what's happening is you're actually guiding the development of your software by writing tests. So it's like, I'm not sitting down and saying, it's like, oh, I think I should do it this way, so I'm going to write a whole bunch of code and then hope that it works and try to test it into working properly. I'm actually going to sit down and say, it's like, all right, how would I write a test case for this given user story? So if I go back to my principal, or if I go back to my admin thing, my admin use case, and say, it's like, okay, I want to mark this collection of images as public so that they can be accessed by anybody who's authenticated. How would I write code that would test that? And then that makes you think about the API that you're going to provide to your software to you know, define collections of images in whatever underlying storage mechanism you have, and then to mark them as public so that they can be accessed. And then, you know, then you can write up a test that says, okay, if I had this software, if I had this API, this is how I would express that. And then, you know, you guide, that's actually guiding the design of your API and the structure of your software, because you're thinking about writing these tests a priori. So we'll go another layer down. We could spend like the whole time going through just some simple examples of how to do this stuff in sort of like a hands-on demo. But there are tons and tons of YouTube videos out there that probably would do a better job than I would do, you know, putting it together, and it would just be redundant anyway, because there's a lot of that information out there. So it's another thing that you can Google, is how the details of how you actually do this. But at a high level, the way you do this is you do what I just suggested, is that you fail first. So you're not going to write any production code. You're going to think first about, it's like, well, what if I had, what would the API to do this look like? And so now I'm going to write a test in terms of that API now. And it may be possible that it's like, well, okay, well, I don't have that API. So that code isn't even going to compile, or it's going to give me all these errors, which is, that's kind of your first failing test. So then when you actually provide those APIs, they're probably just stubbed out. They're probably just, you know, classes that you've defined, or methods, or functions that you've written. And now you can compile your test, but it still doesn't work, because those things all just return an error, or they return nil, or they return, you know, some unuseful value. So your unit test is now failing, but you have a unit test that builds and it fails, and that's your first step. So you've actually made progress. And so now you're going to go back and work on writing enough production code to actually make that pass. There's that minimum fail thing is sort of like a stricture that says it's like don't write anything more than what you need. So again, keep it simple. Just write enough of the test to make it fail. So you've figured out how to what the API might look like. Write enough of a unit test using the stub.api to make it fail. And then you're going to write enough production code to make it pass. And you do this iteratively. So you keep doing this and doing this with more user stories or to complete a given user story. And then now you're going to have a pile of code. And the code isn't going to be the prettiest code that you've ever written, but it's going to be code that is pretty thoroughly tested in terms of the user stories that you've written and that you're working from. And then you take the final step, which is another feedback loop that says it's like, okay, now I'm going to refactor this code. So it's like I have this code. It's not great code. It's there's a bunch of duplication in it. There's a bunch of repetition of variables and stuff like that I've got in there. They're called code smells. Again, that's another thing that you should Google. And I don't say that just because I'm wearing the shirt. But anyway, that's another thing that you should Google and look up code smells. And then you refactor, you remove all that stuff. Your tests are still passing. This is another reason that you've written all these tests, is because now I'm refactoring this code, which means I'm changing it and probably restructuring it. So how do I know I didn't break it? Well, because my tests are still passing. So it's like you keep running these tests, and it's like I said, I'm a huge believer in this, just because I got stuck with making some pretty massive changes to some code while I was working at IBM. It took me about 4 months to get through it. So they were running tests on this large system. I was the only developer supporting it, and they kept filing bugs. I kept fixing the bugs and adding the features that they wanted to in rapid succession, and running my tests like hundreds of times a day. And because I had this huge suite of tests, not all of which I wrote, it was some really nice software that had it came with a lot of unit tests. I was able to, one guy to do that work and keep up with a team that was generating a lot of requirements, because I knew that I always knew if I had broken something, and if I didn't break something, then I knew that I could go on to the next feature. So anyway, that was my experience with it. And again, this is a nice statement that I like from Ward Cunningham. This is sort of like the goal of refactoring. You always want to have the cleanest code possible. You could riff on Einstein and say it's like you want your code as clean as possible, but no cleaner. So you can always polish code and make it even shinier and even tighter, but you need to have a good sense of when it's good enough. And this is one of the criteria for determining when it's good enough. And I always enjoy this statement. Okay, so that's a very high level whirlwind tour of what testing looks like, and in particular test-driven development. There's also something called acceptance test-driven development. Again, it's a thing that you can Google. If you're actually writing production code that's going to go into a product that maybe somebody's going to spend money on, then that's something you should definitely investigate and learn more about and consider adopting, because acceptance test-driven development is very valuable when you end up in contractual situations where somebody's paying you money to develop software and to actually have a product delivered to them, and they want their software and you want to get paid, and it's important to have sort of like a neutral third party, if you will, or an agreed upon standard that says it's like, okay, when all these tests pass, at this acceptance test level, not just the unit test. No customer with a clue is going to sign a contract that says, yeah, when all my unit tests pass, then everything will be fine and you'll pay me money. They're going to require more than that from you. And acceptance tests, large scale sort of system functionality scale acceptance tests are a great tool for that, because it can be pretty unambiguous. Either they pass or they don't. Either the client agrees that, if this test passes, then you will have delivered the functionality I asked for or not. So again, that's something to look into and to follow up if you find yourself, in a situation where you're actually doing software with, contractual obligations associated with it. Okay. Oh, one more thing. I'm sorry. On testing. So that's a lot of that was a lot of design stuff, and it's like you could look at that as just value in and of itself. This is sort of like the thing that helped me not die while I was working through that 4 months of 12+ hour days. My wife was not terribly happy with that whole situation, but we got through it. The key was that, the tests were guiding the development of the new features that I was building. The tests were also, every time somebody would submit a bug or ask for a feature, I would write a test that said, it's like, okay, this test either reproduces the bug, or it captures the feature, and then I would make those tests pass, and then it would go to my CI/CD server, and if all the tests passed, then I could ship that software, I could commit that software and work on the next thing. So basically, your tests are guiding your development. They're also governing your deployment in your CI/CD. So it's basically telling you, it's like, okay, you can commit this software and move on. Okay. So now, having made that segue into, we need to talk about version control, which this is a skill that everybody needs to have. You need to have facility with version control in general, probably with Git and GitHub in particular, because you're probably going to be dealing with a lot of open source software. You may even be contributing to some open source software. And when you find yourself in that situation, you need to have skills with version control. So let's look at what version control does in general. So basically, it's going to allow you to work simultaneously. So if you have multiple people working on a project, you'll need to be able to, you need to be able to make independent progress at the same time. There's going to be conflicts. You're going to change something that somebody else was depending on, or, in the worst case, two of you are going to change the same file. That's always fun. But so you're not always going to avoid those conflicts, but you are going to be able to resolve them. So first, you'll become aware of them before suddenly the software doesn't work. And second, you'll be able to resolve them. The other thing is you're going to archive everything. So it's important to never lose stuff. I learned that was actually my introduction to version control way back in the day when I got out of grad school, and I was working at the first startup I was working at, and I thought it was very cool, and all the hard work in grad school had been worth it, because I was working with guys from Stanford and Berkeley and San Francisco on some really cool software. And then I spent like 2 days writing code and doing a feature, and was pretty close to done, and thought that everything was fine. And I wanted to clean up some directories, and I cleaned up the wrong directory. And 2.5 days of work were gone, and I had to basically spend a lot of time, a lot of late nights recreating that 2.5 days worth of work, and I probably did not do as good a job as I had done in those days. And so basically that was kind of inexcusable that I had a graduate degree in computer science and didn't know how to use version control properly, but that's the way that it was at the time. And so after that, I never did anything that wasn't version control. So you want to archive everything. And the other thing you want is a detailed history of what has changed. So if it's just you working on your software, you may get to a state where you're kind of scratching your head and saying, it's like, this used to work, it doesn't work now, what did I change? That's always fun. Or there's this cool feature in Git that when you're working on a project with multiple people, it's called Git Blame. And at Google, they try to practice what's called no fault code reviews. So when something breaks, you don't want people running for cover or lying or prevaricating about what happened. You want people to own up to it and say, yep, I made that change, I screwed it up, we'll fix it, and then you move on. And that's one of the cool things about Google's culture is that we have that. Not every place has that, and so at Google, you can use Git Blame, and you can say it's like, hey, where'd you change this? Why'd you change it? And did you understand that it was going to do this? And it's kind of blame free. In other environments, it can be used more punitively. So people have been known to pull up a Git Blame thing and say it's like, oh, this person made that change. We're going to kick him off the team, or we're going to make him the goat somehow, which is never fun. But it is valuable to know who made these changes, because sometimes in a security context, it can be very valuable to understand that it's like, oh, somebody has made a nefarious change in this software. I need to know who that is, because there may be legal ramifications for that. So anyway, that's why you need, one of the reasons you need that detailed history. So excuse me, back in the day, all version control was centralized. So you had a central repository, a single central repository, often exposed on a server that everybody had to connect to. If that server went down, that basically meant, well, I can't actually do any work because I can't commit my code, I can't pull new code, I can't do any of that kind of stuff. Distributed version control systems like Git and Mercurial and some other darks was one of them, were really kind of a revolution in the software development world. For most of you, this is just historically interesting because that's really all there are right now is distributed version control systems. But it's good to understand that it wasn't always that way, and there are like actual engineering reasons for why we have distributed version control and why it's so much better. And these are some of those reasons. So the first one is when you're using Git, excuse me if you already know all this stuff, but when you're using Git, everybody has a complete copy of the whole repository. So you can be off and you can just decide, it's like, well, I'm just going to work over here in my repository like it's my own private Idaho. I'm going to create a whole bunch of branches. I'm going to delete them. I'm going to do all of this crazy stuff in my own personal repo, and it's not going to impact anybody else until I actually am ready to publish those changes. And then if I'm a good developer, when I go to publish those changes, I'll clean it all up. I'll kill all those branches. I'll squash all of my extraneous goofy commits, and I'll commit something that looks pretty rational to the rest of the central repo that the rest of the team can then pull from, and they won't think that I'm maybe as crazy as I am. The other thing you can do is you can work offline. So you can go to a Starbucks and have sort of minimal Wi-Fi. You can work on an airplane where you have you have Wi-Fi that you can send email with, but you can't actually do any real work with. Or you can just have no Wi-Fi at all and still be working on your code as long as you have power for your laptop. which is that's a very powerful thing. And again, it's something that you couldn't do back in the day. The other thing is that that was one of the key insights in these distributed computer or distributed version control systems was the old ones, the centralized ones, they were kind of optimized to branch. So you could create branches really easily. Merging was kind of a pain, and people put it off and they didn't like it. And it you know, usually what happened was it's like, okay, all 8 of the developers on the team ended up in a room going through, you know, having a merge day. We called them merge fests, where people would bring all their changes and they would get all their changes merged into the central repo so that it was back in a usable state. That was never really very fun, and it was mostly because the systems weren't designed to make merging easy. One of the things that the distributed version control systems did was they said, it's like, what do developers do a lot? Well, they merge code a lot, and so let's make that easy. And so that was you know, a key design point, and they've succeeded pretty well. There's actually been some, you know, some interesting, you know, graduate level computer science work done on, you know, how to further simplify merges, but they've done a good job of making it up. And then the third one, or the fourth one, is the fact that, you know, because everybody has a complete copy of the whole repository, everybody basically has a backup of the repo, so things kind of never go away. Okay, so there's a couple of models. We're running short on time here, so I'll go quickly through those. So when you're using Git or Mercurial or some other distributed version control system, you'll probably be using Git though. You have a couple of options for how to structure your repos and how to actually commit your changes to those repos. And the first one is called trunk-based development. So you'll hear that term, trunk-based development. And what that basically means is you have the trunk, or it'll probably be called master, and everybody commits to master. And so it's like, when you make a change, you commit it to master. When I make a change, I commit it to master. How do we not have conflicts? Well, it's like, you know, before I commit a change or you commit a change, we're going to pull master and do a merge there of all the changes that I haven't accumulated in master, and then I'm going to push my change up to master. There still may be a conflict. I may still have to resolve some things, but that's basically the way that it goes. It's probably one of the simplest possible workflows. And then in master, I guess in the diagram, you know, at periodic times when you decide, it's like, okay, I want to release the software at this point in time, you create what's called a release branch, and then you do some minimal committing to the release branch. And so then, you know, when you want to, if you have a bug fix, say in version 1.1, then you can actually make those changes on the release branch. And so you can track changes to 1.1 while you've still got, you know, 1.2 or 1.9 still in flight. But the workflow is very simple. You're always committing to master. It ensures continuous development because it's like, I'm not going to be sitting off in a corner, never committing any of my software on my own little precious branch and not pushing it to master, because if I do that, everybody's going to hate me and I'm going to hate myself, because it's going to result in a merge fest, which nobody likes. You know, that's the next bullet, is basically you're going to prevent those kinds of things, because there's enough social pressure that people don't want that to happen. It does require disciplined developers, so people do actually have to know what they're doing. You can't have, you know, a junior person or some cowboy who just decides, like, yeah, I'm just going to commit this to master and I don't care if it breaks. That attitude is unacceptable in a trunk-based development environment. And it tends to work better when you don't have a ton of code, when you don't have a ton of history or a ton of releases sitting out there, and you know, so that you can make changes to the trunk easier. As time goes on and software accumulates more releases and history to it, the resilience of the trunk can can go down. So there's like, it becomes now I can't be so cavalier about making changes to master. Now I have to be much more careful. And that's when you may come into a model like Git Flow, which this tends to be used in like, you know, professional development projects that people are using for well, they do it in open source, but that's what I've used in commercial software development too, just because, you know, we have to have a lot more process wrapped around it. So just briefly, what you're doing is, you, rather than having a trunk, you still have a trunk, whereas it's over here master, but you have a development branch, and that's basically where things get committed. But they get committed from feature branches that each developer is working on a feature branch. He's committing those to the develop branch, and then those, when it comes time to release the software, you're creating release branches that ultimately, when the release is all buttoned down and you're happy with it, that actually gets pushed up to master. So again, Git Flow, if you find yourself in that kind of an environment, or you're working in an open source project that's using Git Flow, you definitely want to explore that. So yeah, so don't lose stuff. You want to track all the things. GitHub is really good about, it allows you not just to track your code, but features and defects as well. And then you do want to think about and settle on some kind of a workflow, trunk-based, Git Flow-based. You can make modifications to it, but you're probably, if you try to invent your own, you're probably making a mistake. Okay. Very quickly, I'll go through this. Like I said at the beginning, the whole reason we're doing this is to deliver stuff. So it's important to deliver stuff. There are a couple of approaches. Well, there's, again, professional software development, commercial software development tends to these days use what's called release trains. So it's basically, it's like, okay, we want to release on, we're going to cut a release on this date. These features are going to be in that release. This feature is only half complete, so we're going to put in what's called a feature toggle for that. So it's turned off in this initial release, but the code is there. And we're going to release these on a cadence. In this particular diagram, it says, we're going to release this every week. It could be every month. I think the Golang project releases like every 6 months. I think Chrome releases every 3 or 6 months as well. And they all run on these release trains. They may or may not use feature toggles, but that's the key, because otherwise you'll just keep accumulating these half-done features and you'll never release anything. So you actually have to put a stake in the ground and say, it's like, on this date, yea verily, we're going to cut a release, and then no more changes are going to go into that release branch, and we're going to actually release this software. So you establish that cadence, you define the features that are going in there in terms of user stories, and then you create your branch, and then you actually release the software. The other thing that's critically important to be able to do that and enable all that stuff is to have some kind of continuous integration and deployment feature. And I was afraid I wouldn't end up with much time to talk about that, and I haven't. So we'll go on from there. I do want to answer questions if people have questions. I've spent a lot of time talking, and now it's your turn. Thank you.
Thanks, Ward. So I saw one question in the chat that I'll just repeat. Someone asked, what is the difference? It was back during your section on using version control. Okay. The question was, what is the difference between committing to master and merging to master? And I think that question was asked on your slide with the trunk based.
Okay. Yeah. So typically what merging is would be something that if I'm working on a branch in my own repo, I may be working on the master branch in my own repo. Excuse me, in a Git environment, I would merge down. So it's like, I'm going to pull all the changes down from master that are up there that I haven't necessarily incorporated into my thing. And then I'm going to make a commit, a local commit to my local master branch. And then I'll push that back up to master. And so it's that's kind of the difference. Is like committing is what happens in a particular repo, whether it's my local repo or the remote repo. Merging is when I bring something from from another source into my repo.
Great, thanks. There's another question in the chat, and I think everyone here are panelists. So if you want to just unmute your mic, you're welcome to just speak up and ask the question, but I'll just read the question in chat as well. There's a question from Arash. Do companies prefer SVN or Git?
It really depends on the company. I think just about any startup that you run across is going to use some version of Git. Older companies, more established companies with maybe an established legacy product, they may use SVN, but for the most part, knowing Git is going to take you pretty far.
Are there any other questions from anyone? Feel free to just unmute and speak up if you want.
I have a question. Do you have you recommended a couple of books, which I thought were interesting. I was wondering if you had a recommended source for learning how to write your code in such a way that it has a lot of unit tests. That's something that I find difficult is, if you have a fairly complex code, a lot of the code the examples that I see writing unit tests are something where the code has been divided into, pieces that are almost trivial.
Right.
And then the tests are almost trivial, but then it's hard to figure out how if you're trying to do something.
Yeah. No, that's an excellent question. Books, unfortunately, tend to be biased towards the easy things because those are easier to explain. The way to find the best source for that is to find a project that has really good testing associated with it, and actually read those tests. So I've learned a lot. Like I said, I'm a Go programmer, and so I've learned a lot from just looking at the Go test suite, because they have a lot of tests for it, and they're non-trivial, and so you can go and look at those and say, it's like, oh, this is how I would do that. So you can do similar things for a good open source project. Now, if your project doesn't have a lot of tests, then you're kind of stuck. But really looking at actual, looking at the test suites for real software is kind of invaluable, because it can teach you a lot.
Thanks.
Sure.
There was another question in the chat. For production code, it seems that, just a comment, maybe this isn't a question. For production code, it seems that branching is used over, say, forking the repo and submitting pull requests. Sorry, that wasn't a question, I think.
Yeah, and that's true. And some of that is a GitHubism, because it's like if I'm working on production code or even an open source project, unless you're a recognized committer, you probably won't be able to commit in that repo. And so, like I said, that's a GitHubism where you fork the repo, you make changes to your local repo, and then you make a pull request back to it. And they may say, it's like, wow, this is great. Do you want to be a committer? Or they may say, it's like, who is this guy? Why is he committing, or why is he sending me this pull request? If they have that attitude, it's probably not a very good project. But yeah, that's the way those things tend to go.
Okay, great. Unless there's any last minute questions, we're running up on time here. So everyone, please remember to share your feedback on this webinar. Rosie sent out a link. I think, Ward, is there also a slide with the link?
Yeah, it's right here. There, that's the one.
And Rosie just sent it out again in the chat. So everyone, please go ahead and do that. It'll be really quick and is really helpful. So thank you, Ward.
Oh, you're welcome. Thank you.
Great. Thanks everyone for joining in.